Hello and welcome to today's chemistry video. I am Christian,
And I am RG.
and today we will be discussing buffer solutions and the Henderson-Hasselbalch equation. Let's start with the buffer solutions. First, what is a buffer solution?
A buffer solution is either a mixture of a weak acid and its conjugate base, or a mixture of a weak base and its conjugate acid, both of reasonable concentrations and must be of weak to moderate strength.
They resist changes in pH when small amounts of a strong acid or a strong base are added.
There are two types of buffer solutions: acidic buffer solutions and basic buffer solutions.
An acidic buffer solution has a pH less than 7. Acidic buffer solutions are commonly made from a weak acid and one of its salts, often a sodium salt. A common example would be a mixture of ethanoic acid and sodium ethanoate in solution.
Basic buffer solution is the opposite. It is a solution which has a pH greater than 7. Basic buffer solutions are commonly made from a weak base and one of its salts. A frequently used example is a mixture of ammonia solution and ammonium chloride solution.
Okay, so how do acidic buffer solutions work? We'll consider our earlier example of ethanoic acid and sodium ethanoate. Ethanoic acid is a weak acid, and the position of this equilibrium will be to the left. Adding the sodium ethanoate to this solution adds a lot of extra ethanoate ions, and according to Le Chatelier's principle, that will tip the position of the equilibrium even further to the left.
This means that the equilibrium is not balanced. There would be more reactants than there are products, which we would have to rebalance in order to achieve equilibrium.
So far, we have unionized ethanoic acid, ethanoate ions from the sodium ethanoate, and enough hydrogen ions to make the solution acidic.
In adding an acid to this buffer solution, the buffer solution must remove most of the hydrogen ions, otherwise the pH would drop evidently.
Hydrogen ions combine with the ethanoate ions to make ethanoic acid. Most of the new hydrogen ions are removed in this way.
But in adding a base to this buffer solution, basic solutions contain hydroxide ions, and the buffer solution removes most of these.
There are two processes which can remove the hydroxide ions. One, removal by reacting with the ethanoic acid, where they would form ethanoate ions and water.
Or 2, removing by reacting with hydrogen ions, where they combine to make water, which when happens, the equilibrium tips to replace them until most of the hydroxide ions are removed.
How about the basic buffer solutions? We'll consider the mixture of ammonia and ammonium chloride for basic buffer solution. Ammonia is a weak base, so the position of this equilibrium will be to the left. Adding ammonium chloride to this solution adds extra ammonium ions, and according to Le Chatelier's principle, that will tip the position of the equilibrium even further to the left. Again, this means that there is no equilibrium. In order to regain equilibrium, there should be lesser reactants than the products.
We now have unreacted ammonia, ammonium ions from the ammonium chloride, and enough hydroxide ions to keep the solution basic.
Yay!
If we add an acid to this solution, there would be two processes to remove the hydrogen ions that was added.
1, by reacting with ammonia, where most of the hydrogen ions would collide with an ammonium molecule to form ammonium ions.
Or 2, by reacting with the hydroxide ions where they would combine to make water. And as it happens, the equilibrium tips to replace the hydroxide ions until most of the hydrogen ions are removed.
But if we add base to this buffer solution, the hydroxide ions from the base are removed by reacting with the ammonium ions.
Because the ammonia formed is a weak base, it can react with the water, which means most of the hydroxide ions are removed from the solution. What is the Henderson-Hasselbalch equation about?
The Henderson-Hasselbalch equation is an equation deriving the pH of solutions, created mixing known amount of acids and conjugate bases or neutralizing part of acid with a strong base.
This is the Henderson-Hasselbalch equation. Okay, so how is it used? We have a sample problem here to demonstrate the use of the Henderson-Hasselbalch equation. 0.20 moles of benzoic acid and 0.10 moles of sodium benzoate are dissolved in 1 liter of pure water. What is the pH of this solution? We are given the acid dissociation constant of benzoic acid, which is 6.3 times 10 raised to negative 5. So, how will we use the Henderson-Hasselbalch equation? We have the following given data. First, let's write the equilibrium equation. We'll represent the acid with HA, which will be in equilibrium with H plus and A minus, which represents the conjugate base. We will now proceed to the ice table. The acid, as given, has an initial of 0.2 molars. The H plus is initially 0, and the conjugate base has an initial of 0.10 molars. Next, we need the pKa of the acid. It is the measure of strength of the acid, and to get this, we will be getting the negative logarithm of the acid dissociation constant. From here, we can plug in the value of the pKa to the equation, giving us 4.202 plus the logarithm of the initial concentration of the conjugate base all over the initial concentration of the acid. This gives us pH is equal to 4.202 plus negative 0.301, which gives us a pH of 3.901. And that is all you need to get the pH of a solution using the Henderson-Hasselbalch equation. Thank you for your time here in our chemistry video.